Okay, so let's have a look at some different simple discrete time signals. These are fundamental signals which have a lot of uses in signal processing. So our first example is the unit sample signal. So this will be the unit sample signal. In all cases, the x-axis refers to the time index and the y-axis refers to the amplitude. So we have in this case the unit sample signal which is an impulse in discrete time. Because of that reason, we represent it using delta n, which is 1 if n is equal to 0 and 0 otherwise. It's one of the most important signals that we're going to see. So the unit sample signal has many uses, and you can see now that the unit sample signal is indeed 1 when the time index is 0, the value is 1, and everywhere else it's 0. Okay, so our next signal is the unit step signal. Unit step signal. Okay, so unit step signal is represented by the letter U. U of n is equal to 1 if n is greater than or equal to 0 and 0 otherwise. So this function is the discrete version of the Heaviside step function. So it is called the unit step signal. And you can see that it is 0 up until the time index 0, and after that it becomes 1. So it's just a small section of the signal. Okay, our next signal is the unit ramp signal. There isn't much space here, but I'm going to just write it. Unit ramp signal. It is represented by the letter R. So R of n is equal to n for n greater than or equal to 0 and 0 otherwise. So that is, we have a signal which linearly increases after time index 0 is reached. And finally, another very important signal, which is the exponential signal. Okay, so the exponential signal is just a signal which is actually exponential. So we have some a to the power the sample index. So for the specific case, what you see is, let me write it with a different color, doesn't matter too much, but yeah, so this signal is x of n equals to 0.9 to the power n. So how does it look like then? When the time index is 0, the value is 1, then it's 0.9, then it's 0.81, etc. It goes on like this. And obviously it doesn't have a piecewise definition, which means the signal diverges when the time index is negative. But specifically for this 0.9 to the power n case. So these are some simple discrete time signals which we can use for many different things. Exponential signal may not be clear immediately what kind of a use it may have, but we'll see that when a is a complex number, and more specifically when a is a complex exponential, sorry, when x of n is a complex exponential signal, we have many uses for it. Most notably, the discrete time Fourier transform and discrete Fourier transform. Okay, so we can categorize signals based on their different properties. So one such classification considers whether a signal is an energy signal or a power signal. So an energy signal has a finite energy. So energy is defined as in here. So we get the square of the magnitude of each of our samples, and we sum that over all possible samples. So that is the energy. And the power is defined as the energy in a specific region in time or in sample index from minus n to n, averaged over that same duration when n goes to infinity. So at the limit where n goes to infinity. So that is power. Obviously, if we have a signal with a finite support, that means a signal with a finite time support, that is a signal which has a finite duration, then it cannot be a power signal. So then the energy signal is a signal where energy is bounded between 0 and infinity. It obviously is positive, so it can be, it should be greater than 0, and obviously it has to be bounded, so it needs to have some upper bound, so it cannot be infinity. And for power signal, it's the same for the power of the signal. So these are two different types of signals, but there is one little note here which I should add. I'm going to add that note here. Okay, so if we define let's say partial energy E sub n as n from minus n to n, so that is the second part for our power, x of n squared, then E is given as En as n goes to infinity. Okay. And P, power, is as n goes to infinity 1 over 2n plus 1 En. Then again, as I just mentioned before, just put it here, if P is 0, so we have a signal whose power is 0, then the energy will be bounded. So that is something which is typical of this duality, that is energy signals and power signals, so this categorization. Okay, so another type of classification involves whether a signal is periodic or aperiodic. So a periodic signal is a signal for which there is an n, there exists an n such that the signal repeats itself with that duration. So that is, there exists an n such that the value of the signal x at its sample n plus kn is equal to xn, which means xn is a periodic signal. And the period is, the fundamental period is the smallest n that satisfies this condition. So if there is no such period, we call our signal an aperiodic signal. So, Let's give a little example. Actually, we talked about this before, but let's just write that once again. There's no harm in repeating some of the stuff. So if x of n is a sine 2 pi f0 n, x of n plus n is a sine 2 pi f0 n plus 2 pi f0 capital N, the period. So in order to have this relation, x of n is equal to x of n plus capital N 2 pi f0 n, apologies, 2 pi f0 capital N should be equal to 2 pi k, where again k is an integer. Which will then mean that, and this is kind of an important result, f0, the fundamental frequency of our signal, is a rational number. So that is an important result. I'm gonna just yeah, that's not gonna work out, so let's just draw it with red this time. So that is the fundamental frequency of a discrete time periodic signal is a rational number. That's the result from this discussion. Okay, another way to categorize signals is by way of their evenness or oddness. So an even signal is symmetric with respect to the time origin. That is, if x sub e is an even signal, and in this case we're looking at x sub e of n, okay? So if you have an even signal, then its value at the time index n is equal to its value at the time index minus n, that it is symmetric with respect to the time origin. And obviously the value at the time index 0 is not dictated by any condition, so it can be anything really, because x even of 0 is again x even of 0. And another type of signal is the odd signal, where the signal is antisymmetric with respect to the time origin. That means x odd of n is equal to minus x odd of minus n. And this signal is x odd of n. Now, a nice property which we can use, which in fact we will use later, is the fact that we can decompose a signal into its even and odd parts. So let's just write this. X even of n is equal to 1 over 2 signal x of n, and this can be an arbitrary signal, by the way, plus x of minus n, okay, and x odd of n is equal to 1 over 2 x of n plus, minus x of minus n. It is clear that if you add an even signal and an odd signal, it's going to end up as being, the result is going to end up as being our original signal x of n. That means we can just represent any signal by using an even part and an odd part. So this is, let me just write it as a little note here, little explanation. So this is how to obtain even or odd signals from an arbitrary signal. X of n. Okay, so even and odd signals. So we have just started looking at different operations on signals, and we have to talk about them as well. So the first operation is that carries a lot of importance actually in filtering, in many things you do actually. Array processing, if you like, audio processing, any type of temporal signal will have to deal with some sort of delay. So that is the delay operation. So let's just write what a delay operation is. So delay operation is y of n, x of n delayed by k samples, where k is an integer. And yeah, k is greater than 0. Okay, so much so for delay. So let me just put it a little bit here. Okay, so let's have a look at our example. So this is a ramp signal, as you can see. So this one here is R of n, a ramp signal. And this one is R of n delayed by one sample. That means our signal starts not at 0, the time origin, but it starts at 1. So we have shifted our signal by one sample to the right. Okay, so when k is negative, that's the same story. I mean, nothing too exciting there. So we have y of n is equal to x of n plus k, which is the time advancing our signal. That is when k is again an integer and k is greater than 0, so that means we are advancing our signal. That is, we are shifting to the left. So in here you see such an advanced signal, time advanced signal. So in this case our signal starts non-zero values, or the time origin for our signal starts not at 0 but at -1. So this is -1 and this is R of n plus 1. Okay, so far so good. I mean, this is not as much exciting as you would think, probably. Time reversal, we're just getting the symmetric version of our signal with respect to time. So time reversal is y of n is equal to x of minus n. That is something we did just a moment ago, right, for calculating the even signal and the odd signal. So this is r of minus n. What happens is, oops, I'm sorry, so this is, so we've shifted minus n minus 1. Okay, so this is the signal which is flipped with respect to time. Okay, so time scaling, where y of n is equal to x of capital K n. In this case, well, k can be any integer, but in our example it's 2. So this is the ramp signal time scaled by 2, which means when we carry out this operation, say y of 0 is x of 0, y of 1 is x of k, y of 2 is x of 4, etc. Okay, so that means that our time axis gets squeezed. So you can see that in all the other examples, we have, yes, I don't know what happened here, I need to remove it. Okay, so we have just, so r of 2n is this. So you can see that the time index is from -2 to 2, whereas in here it's from -4 to 4. So we've just squeezed our time in this. For some reason, time scaling has also went away. Okay, so k of n. Okay, so and finally amplitude scaling, which is the simplest and most boring one of all, but that is also useful. Y of n is equal to a times x of n. So we're just multiplying our signal with a gain. So in this example, it is 0.25 r of n. Okay, so we've just scaled our signal by minus 0.25 r of n. So these are different types of operations on signals. There are many others, but these are the most common ones. Okay, so we can design systems which can carry out a combination of these operations on signals to achieve useful results. So this is the point at which we go from signals to systems. So obviously you can design systems which combine these different properties, which do certain important stuff, mainly filtering, but many other things as well. And so this brings us to the topic of linear time invariant systems. So we represent a linear time invariant system, or we can represent a linear time invariant system by using some operator q of something. So in this case, q of x of n, it's going to be. Okay, so what is time invariance? So if you delay or advance the input to a system, and if the result that you obtain, if the output that you obtain from that system is delayed by that same amount or advanced by that same amount of time, then you have time invariance. So this is a time invariant system. So that means if you shift your input by k samples, if you delay your input by k samples, the output will be delayed by k samples as well. Okay, so that is pretty straightforward. And how about linearity? So if you input a linear combination of signals to an LTI system, the output is a linear combination of the outputs of the signals that correspond to these inputs. So what do I mean by this? So let's write it down. So let's say So let's say you present you input signal x1 of n to your system, and the output is y1 of n, and you present x2 of n to your system as an input, and the output is y2 of n. Okay, so if we present a times x1 of n plus b times x2 of n to our system as an input, the output will be a times y1 of n plus b times y2 of n. So this is linearity for you. So some examples. of linear and nonlinear systems. So yeah, so let's define a system which is time invariant but not linear. So this is q of x of n is equal to x of n squared. So this is time invariant, but not linear. And how do I know that it's not linear? Now, if I present, say, for instance, x of n plus q of n as an input, then the output will be x of n squared plus q of n squared plus 2x of n q of n. So there will be another term which doesn't fit the bill. So that is a nonlinear system. What about this? Use a different color for that. So just use green. I'm hoping that it's going to be visible, or let me just pick another color. Yeah, orange one. Okay, so yeah, so let's say we have another system which is responding by the time index, the argument of our signal, the time index of the signal. So this is then time variant. And finally, let's give an example of a linear time invariant system. Okay. So it is q of x of n is equal to x of n plus x of n minus 1. So this system is linear and time invariant. In this course, we are specifically interested in linear time invariant systems because these are the classes of systems which are most relevant within this level of signal processing. So obviously there would be many different layers to signal processing. There may be nonlinear approaches, nonlinear signals, nonlinear systems. So there may be many different things, adaptive systems as well. But in this case, we're dealing with linear time invariant systems only. With adaptive filtering, we're going to go into time variant systems as well, but that's a different story altogether. Okay, so another way to categorize systems is causal and non-causal systems. So we have linear time invariant systems, time variant systems, nonlinear systems, but in this case we're looking at a causal system and a non-causal system. So what is a causal system? A causal system is a system whose output depends only on the present and past values of inputs. So what do we mean? For instance, let's say that our system takes x of n and produces a y of n, which is x of n plus x of n minus 1. Okay? So that means for calculating y of 5, I need x of 5, the signal x, the fifth sample of x of the signal x, and the fourth sample. Okay? So we're using previous samples of our signal. So that results in a causal system. So just think about what causal means. It means the output is caused by the input. So we need to wait for the input to arrive before even processing it. So that is a causal system. So what is then a non-causal system? It is a system whose output depends also on the future values of its input. Now, for real-time signal processing, obviously, it's in many cases, it becomes a bit of a problem because, well, just think about this. We are dealing with a system whose output depends also on the future values of its input, which means we need the future values of our input to produce output. In many cases, you don't want to deal with such things, such a system, because especially if you're dealing with your signal sample by sample, you don't have the next sample. But when you're dealing with your signal buffer by buffer, say, for instance, your sound card gives you 512 samples, then you can emulate a non-causal system, although you will be introducing an additional delay. But that's something which you shouldn't worry at the moment. So let's just define a non-causal system. I'm going to just write it here. The output, y of n, is a combination of a future value plus, say for instance, a past value, x of n minus 1. So again, we're dealing with a future value in here. So this is a future value of x of n. So the system on the right-hand side then is a non-causal system. Now, non-causal systems can also come in different shapes. You may have, for instance, an anti-causal system, which would depend, but for which the output would depend only on the future values and not the past values. Then you have an anti-causal system. So that's a different type of a system. Now, you can also categorize your systems based on their stability. So stable versus unstable systems. Now, there are different definitions for stability in different contexts, but we're going to deal with only one, that is bounded input, bounded output stability. Now, whenever you're stuck, think about the meaning of this term. I mean, there are many terms that we're going to learn throughout this course, and this is one of them, BIBO stability, bounded input, bounded output, which says if your input is bounded, your output is going to be bounded. Then you have a BIBO stable system. So a system whose output is bounded for a bounded input. That is a BIBO stable system. And definition is quite simple. As in many things in signal processing, concepts start at really simple places. So this is the definition, x of n, the absolute value of x of n, is less than some upper bound, mx is less than infinity, so there is an upper bound, an actual upper bound. And if for that input the output, the absolute value of output, is also bounded by some other upper bound, my, then we have a BIBO stable system. Okay, so how about giving an example? So let's have a look. Y of n is equal to 2y of n minus 1 plus x of n. Now, how do we know that this is not stable? This system is not, the system which generates this difference equation is not stable. Now imagine y0. So let's say we're feeding this, a unit sample signal. Let's say x of n is equal to delta of n, unit sample signal. Then let's have a look at what y0 of n is. So y0 is 2y minus 1 plus delta n, which is, 1, right? So y0 is 1. Now, we have assumed that the system does not have a state. That means, y of n minus 1 is 0. So let's also write it as a condition so that this explanation makes sense. So y of n is 0 for n less than minus 1. Sorry, less than or equal to minus 1. Okay, so y0 is 1. How about y1? y1 is 2 times y0 plus delta 1. So this is, as we know, is 0. Then the output will be 2 times y0, which is 2, right? So, right, what is y2 then? It is 2 times y1 plus delta 2, which is 4. So the system then has, if we go on and on to y of n, the output is 2 to the power n. Now that's interesting. So the output then does not have a bound. So if you increase n to infinity, then you have an unbounded output. So our system then is an unstable system. Now it's easy to check for stability if you have simple systems like these, but in many cases we're going to resort to different approaches, which are slightly, just a little more complicated than this, but that's okay. I mean, just confirming that the original assumption does not hold, which is the output being bounded, is sufficient to show that a system will be unstable. And we have just shown it for a simple signal, which is a unit step function. I'm sorry, unit sample function, an impulse. And in some cases, it may just be so that the system would be acting as a stable system for the unit sample function, but not for the unit step function or for the ramp function. So we will see some better ways of analyzing stability of systems in a couple of weeks. So we've seen some examples of different systems, and you've seen that there's a commonality. That commonality is the way we're representing those systems. The way that we're representing those systems is by way of difference equations. So we're expressing the output of such a system in terms of a number of previous values of the output. So that is n previous values of the output, as well as the present value of the input, and m previous values of the input. Okay, so this is how you would represent the system. And we're going to see that this representation comes in pretty handy when analyzing systems. Right now, it's just an introduction, say, to representing a system as a difference equation, but we're going to use it quite often later. Now, that brings us to convolution. Now, in mathematics, convolution is the name given to the product of two polynomials. Whereas in many signal processing courses, that aspect of convolution is never mentioned. Right now, we're not going to mention it. Right now, you're not going to be knowing why we have a name convolution for this operation. But you're going to see later, when we talk about the Z transform, that it makes quite a lot of sense to express it in this way. So for convolution, let's try to define what it is. So let's consider the LTI system, linear time invariant system, where the system is represented by the operator Q. Okay, so this is our system. So let's also assume that we can write an arbitrary signal in terms of simpler signals, such that, say, x of n, that's our slightly more complex signal, is written in terms of a linear sum of simpler functions. We haven't defined what simpler is, what simpler means, but just so you know, we can have simpler signals than a slightly more complex signal, or we can express such signals by using more simple signals, like fundamental signals. Now, here is the little trick. Since the system is linear time invariant, its output for x of n, that's our input, can be represented as a linear combination, and the same linear combination of our system to of the output of our system to the simpler signals, xk of n. Which is nice. I mean, up until this point, we talked about simpler signals, but we haven't talked about what these are. Simpler signals, what are they? So which simpler function is a good choice? And the reason why I have, quotes in around simpler is we just don't know what kind of a simpler signal would be a good choice. So let's have a look at this rather arbitrary signal. So this is our time origin, sample origin. This is n, and this is, let's call this signal x of n, if you like. So let me just call it x of n. So these are the samples. So this is 0.5, this is 0.75, etc. Okay? So let me just express the signal. This is 0.25. This is minus 0.25. Okay, so let's just write our signal in terms of, the simplest way that you can write the signal is by way of unit sample signals. So let's try doing that. X of n is equal to 0.75 delta n plus, it's got to be 0.5. 0.5 delta of n plus 0.75 delta of n minus 1. Okay, n minus 1 plus 0.5 delta of n minus 2. I think you got the point. There's no need to write it any further. We're just writing our signal in terms of delta signals, that's the unit sample signals, which are shifted in time. So, for instance, this first one, the 0.5 times delta n corresponds to the first sample here. So this is that. So n equals to 0. So this is for n equals to 1. So this corresponds to this one. N equals to 1. Okay, so this is how we express our signal using unit sample signals. Now there is a little note for those of you who are not very well versed in signal science systems or signal processing. Delta of n minus k is equal to 1 if and only if what? Just think about it yourself. Since this is a video, I'm going to have to tell you what it is, but just think about it. We know that delta n is 0 for n equals to 0, which means when the argument of our delta function is 0, then the value is going to be 1. That means n minus k is 0. That means when n equals to k. So that's the shifted version of our unit sample signal. So in other words, we can express x of n as this, x sub k delta of n minus k, where again, x sub 0, for instance, is 0.5. Yeah, okay, so x of 0 is 0.5, x sub 1 is 0.75, etc. Okay, so this is how we write it. Now here's a little trick which leads to the convolution sum. Using the, okay, here, using the linear time invariant property of the system, we have this, y of n is equal to, for all k, x sub k, q of delta n minus k. Now that's a very interesting point, because by this we have just defined a very characteristic feature of a system, which is its impulse response. I'm going to write it in different colors so that it's more distinct. So h of n defined as q of delta n is the impulse response of the system. Okay, what do we mean? We mean if you present an impulse as an input to our system, it's going to produce the impulse response, the response of the system to an impulse. Now, for computational systems like filters, linear time invariant property is a given. You don't have to worry too much about it. However, for real systems, like for instance the acoustic pad in a room from one microphone, from one loudspeaker to a microphone, we would only have to assume that path, the impulse response for that path, is linear time invariant. It's only then that we are able to do some useful stuff with it. But again, for completely, discrete time signal processing for designing systems, then linear time invariance is something which is quite easy to achieve. So from this point on, we then have the convolution sum. So I just want to move everything a little bit up so that I can write it right underneath here. Okay, so right. Then convolution sum is this. I'm just going to write it here. Okay, y of n is equal to, for all k, xk, but let's write it as xk, age of n minus k. So that refers to the value of the kth element in our signal. This is one way, and the second way is equivalent to saying that y of n is equal to for all k, x of n minus k, age of k. Okay, and in both cases this is equal to move it a little bit here. It's not nice to do that, but I'll have to do that. Let's write it by black here. Okay, so this is called convolution sum. Convolution sum, and by convention we write y of n is equal to age of n, an asterisk, which means convolution by x of n, which is equal to x of n convolved by age of n. That means convolution is commutative. Okay, so convolution sum here. All right, so we have just defined convolution by looking at the most basic property of linear time invariance of our system. So again, so we have these two definitions, which is age of n convolved with x of n. So for all k from minus infinity to infinity, x of k, age of n minus k, or x of n convolved with age of n, which is x of n minus k times age of k. So these are equivalent representations as long as both your signal and your impulse response have infinite time support, that is, they have values from minus infinity to infinity, then these are going to work out. So this is convolution sum. Now, how about another term, causality? Now, again, we have many terms, and I invite you to think about them. In Turkish, causality is nedensellik. That is, something happens for a reason, right? Something cannot happen without reason, or rather, that's another way of telling it. So a causal system is something very similar to or very fitting to this definition. So an LTI system is causal. An LTI system is causal if and only if the impulse response is 0 for negative values of its time index. So in that case, we can define convolution in this way. So y of n equals to x of n minus k age of k, that's the argument for the sum, but k starts from 0 now because all the rest is 0, so we can just have a lower bound for our convolution sum, which is nice. Or equivalently, we can just express it as k from minus infinity to n this time, x of k times age of n minus k. So this is a different type of summation. Now, in this case, we have talked about a system being causal. So how about if the signal that we input to that system is also causal? And that might easily be, right? So if xn is also causal, that is, xn does not have any values when the time index is less than 0, that means it only has values after some agreed upon time origin, then we can express the convolution as a finite sum, isn't here. So we have k from 0 to n, and the same argument for the summation. Okay, so causality and convolution sum, as well as the impulse response. So can we possibly find out if a system is bibostable just by looking at its impulse response? Now, let's remember what bibostability is. We have a bounded input, x of n, which is less than mx, which would lead to a bounded output, which is less than or equal to my, or less than, depending on how you see it. Anyway, you know, it has to be upper bounded, both the input and the output. So let's write first, let's express the way that the output is obtained by using the system. So y of n, obviously we have a convolution sum for all k, x of k, age of n minus k, which is something we have just derived, the convolution sum. What do we want for our system to be stable? We want the output, the absolute value of the output, to be bounded, right? So we have this then. So we want this to be bounded. But we're just not constraining it right now. I'm just going to write a little note here. You may remember from your early days at the university, maybe earlier, I don't know, maybe later, but most definitely in calculus, the triangle inequality. Inequality. That is, the absolute value of x plus y is less than or equal to the absolute values of x and y summed. So let's apply the triangle inequality to this absolute value. Then we have this. Y of n, absolute value, is less than or equal to, for all k, x of k, and age of n minus k. Now, something else we know, k is bounded, so it's always less than or equal to mx, right? So that means we have this relation holding as well. M sub x, absolute value of age of n minus k, which is equal to mx sum over all k, age of n minus k, absolute. Now we want this value, the upper bound of y of n, to be less than infinity. And the only way that this can be less than infinity, this will be bounded, is if the impulse response is absolutely summable. So that means the system is bistable, stable if its impulse response is absolutely summable. Or in other words, for all k, when we sum these values, it is bounded. So this is the condition for a linear time invariant system to be bistable. So we can just show that for any system. So let's give an example, a little example if you like. So let's consider an LTI system which is defined in this way. Okay. So by the way, just also think about whether or not it's causal. It is causal, right? Because we have a unit step function here, which is 0 when n is negative. So this system has an impulse response which goes on like this. It's alpha to the power 0, which is 1, alpha to the power 1, which is alpha, alpha squared, alpha cubed, alpha fourth power, etc. It goes on like this. And when n is negative, for negative sample indices, it's 0. So the question is this: what is the range of alpha for this system to be bistable? So using the absolute summability condition which we have just considered, let's have a look at whether our system is stable for just any given alpha. So let's have a look. So we would like this condition to hold, right? So age of n, which is equal to what? Which is equal to n from 0 to infinity, alpha to the power n. So we've dealt with the unit step function by just changing the summation index, the lower summation index. That means we don't care about values less than, time indices less than 0. Now, again, you may remember from basic maths that this series converges if and only if alpha is less than 1, and converges to 1 over 1 minus alpha. I'm leaving the proof, if you like, to you. It's simple. You may remember it, you may not remember it, but just if you work with all the terms and factor terms, you're going to be able to reach that value that this infinite series converges to. But this only happens if alpha is less than 1. Okay, that means the answer to our question is the system is stable if alpha is between -1 and 1, and -1 and 1 are not included. Okay, so this is a very simple stability analysis based solely on the impulse response of the system. Okay, so let's talk a little bit about different properties of convolution. So unit sample and time shifting. So let's first define our convolution, first of all. So y of n is equal to x of n convolved with age of n. So unit sample, if age of n is delta, x of n convolved with delta of n is equal to x of n. So if you convolve a function, if you convolve a signal by the unit sample, then the result is the signal itself. And also, if we shift the sample by, the unit sample signal by k samples, if we delay it by k samples, the output will be delayed. So this is time shifting. Then commutativity. So convolution is commutative. We have talked about this. X of n convolved with age of n is equal to age of n convolved with x of n. So this is commutativity. Distributivity. So if we convolve x of n by a combination of two systems, h1 of n and h2 of n, we can express it as x of n convolved with h1 of n plus x of n convolved with h2 of n. These all come from linear time invariance of the system. So maybe we should write it right here that our system is linear time invariant. So where age of n is the impulse response of an LTI system. Okay, because that's kind of important. And finally, associativity. Okay, so convolving x of n with h1 of n and then with h2 of n is the same as convolving x of n by the convolution of h1 of n and h2 of n. Now we're going to see later that these two properties are also related to parallel and cascade connections of different systems. Okay, so far so good. And that brings us to different types of systems.